Okay, Pedrini.
Okay, and we're ready to go. Okay, Mario, you can go ahead and get started.
Okay. Okay, guys, you know what this presentation is about, and this is about finding the miter angle for the angle in the miter for the compound miters, and also the tilt. Now, let me say from the beginning, once the presentation is going, and if you happen to have a question, just go ahead and interrupt, and we'll get into and address we'll give an answer to that question. So don't let me keep going, or don't let the presentation keep going if you have something in which you got lost. Otherwise, you're not going to understand then after that point, you're not going to understand what is happening. So any question, just tell, please, I have a question, and we'll pause. Okay?
Okay, and the video lesson itself is on the engineering training page on training content under takeoff training, and under the checking training, that's the checking compound miters with CAD 1. So
before we begin with showing let's say the first image, just let me say something. When we have a compound miter, first of all, we have the information that is going to come in place to, and the elements of that is going to make that compound miter. So we have in this case, we are supposed to have the degree of the slope. We are supposed to have what system we're going to be using, and all of that is already given to us. So the problem is that as a matter of fact, with all that information, we should be able to get anything that constitute as a compound miter, but the problem is that we don't know how to read or where to place ourselves to read that compound miter. So, and that this is probably, hopefully that's what this presentation is going to cover. Okay, let's go ahead, Bill.
Okay, the file that Mario used to create this process, he can put that into a folder if you want to access that and view or practice with that file later. So we'll set up the link for that after the training session as well.
Also, I want to mention, and I want to give credit to Quinton. He helped me to splice all this. There were like a dozen of little recordings, and he spliced them all, and to make sense out of this.
Thank you. I was just happy to help.
All right, well, here we go.
Of the footprints.
We'll bring this back to the beginning.
This video is to show you.
And let me go to the settings, make sure we're on highest quality, and we'll go full screen. Okay.
How to find the miter angle and the tilt in a compound miter through projections using AutoCAD. For this demonstration, let's pick two planes, or more specific, two elevations, that in plan view, they will be joining, creating a 90-degree outside corner. As we can see here, these two schematic elevations, elevation number 1, elevation number 2. Elevation number 1, on a perfectly vertical plane, containing a tilt at its right side edge of 78 degrees in relation to the horizontal plane and 12 degrees to the vertical. Elevation number 2, at a slope following that tilt at right side edge of elevation number 1. To better visualize what we have, let's see the following schematic isometric. As clearly as this shows us elevation number 1, vertical, joining elevation number 2, slope. Now that we have seen all this information, let's start our process. The first step in our process will be to determine the depth of the system we're going to be using to fabricate these elevations. Let's pick arbitrarily a 7.5-inch deep system. For this, we're going to be looking at a series of graphics describing the different steps in the process. First, let's describe what is happening with the system at the elevation number 1, the vertical elevation. Let's call for this line to represent the face of the system and this the back. Distance between the two of them, as we know, 7.5. Now with this step done, let's jump to the next, where we'll be seeing what the system is doing at the slope elevation, elevation number 2. For that, let's rotate this 12 degrees of the vertical plane. Now we have rotated and we have obtained this. Notice the lines have been rotated as a unit, where the distance between the parallel lines is still 7.5. Placing a horizontal line, using green color in this case, we can measure and show the inclination degree of the slope, 78 degrees. Also, we are going to proceed to measure from the face to the back of the system over the horizontal line. And the result, this will be the distance value that we'll be using to create the horizontal footprint.
I just muted. Did this sound stop when I muted myself?
Yes.
Yes.
Okay, sorry. Let me back up. Didn't realize that the sound was coming out of my speaker.
To the back of the system over the horizontal line. And the result, this will be the distance value that we'll be using to create the horizontal footprint at the slope portion. Keeping in mind that at the vertical portion will remain unchanged as 7.5 inches. Now that we have established, as mentioned before, the footprint shown with green line for the sloped elevation with a floor plan or horizontal dimension value of 7.668, we can create what I'm going to call the bottom footprint of the miter corner. This is the plan view, or what I want to call bottom footprint, developed, as you may remember, with values obtained in previous graphics. As you can recognize in the left side of the corner representing the vertical elevation, the 7.5-inch deep system. In the other, the slope side, the 7.668 depth. With this done, we all can see that despite this is in plan view, a 90-degree corner, the miter angles are unequal, as seen here. And just like that, Right here, we have the first piece of the information we were trying to get, the miter angles. With the bottom footprint done, from where we got the compound miter angles, now we're going to make use of this and start working toward getting the compound tilt. Needless to say, a footprint in this case is a horizontal plane cutting through the corner. With that in mind, we'll create another footprint, which we'll call it top footprint, because it's going to be a horizontal cut or section at a higher point than the bottom footprint. Knowing the angle of the slope, we'll make use of this by placing a projection of such slope starting at the outside tip of the corner layout or bottom footprint. Having this projection in place, shown here in yellow color, we follow and place two more projection lines. One green line on top of the face of the vertical side, representing the horizon. This line may be a projection, but is also occupying exactly the same space as the face of the vertical at that level. In other words, this line is also the same as the one in the bottom footprint. The last line that we have placed here is the red line. We can see this red line is parallel to the horizon, and the distance between them is 3 inches as seen in this dimension. The last three lines we have placed here, the yellow representing the slope, the green representing the horizon plane or bottom footprint, and the red line representing a horizontal plane 3 inches above the bottom footprint plane, which is the green. This red plane is where the top footprint is going to be. 3 inches is just a number that I have chosen for separation between the bottom and the top footprints. Those 3 inches could have been 1 inch, 2, or 10 inches, whatever you want. With these three projection lines in place, and knowing that any footprint of the corner along the slope will always be the same, but the location of this will change, moving right as this goes up along the slope. While we are still looking at this image, let me say the next step will be copying the bottom footprint. Moving this toward the right, using the intersection of the face of the slope side with the red horizontal line as the base point. I'm placing this at the intersection of the top footprint, red line, with the slope line. Once this has been moved, change color to red. With those steps done, we can see the new top footprint in red color and in its rightful location. Now that we can see the projections of both the bottom footprint in green and the top footprint in red in the same layout, I can even say twice, because if it's true we are clearly seeing the footprints, we are also seeing the horizontal projections that are 3 inches apart. And those horizontal lines are projections of the footprints. As you know, these horizontal lines is what you will see if you were standing right here perpendicular, standing on the floor perpendicular to the vertical planes. And you will see the green line as a horizontal line starting from this point, and you will see the red line as a horizontal line starting from this point. knowing that these sets of layout are 3 inches apart from each other, now I'm going to be the observant and position myself right here in line with the miter lines of the footprints. Once I do that, I will see those as points. The green point on the bottom footprint, and 3 inches higher and a little bit to the right, the red point on the top footprint. And the moment you have that in front of you, you can make a line between the points, and that will be your tilt. To record that on a clear way, we're going to make a vertical section perpendicular to the miter lines. As long as it goes perpendicular to these 2 lines, which are the miter lines contained on both the bottom and the top footprint. And project that down onto the layout to see and measure the tilt. Here we can see the section perpendicular to the miter lines already projected onto the layout. Now let me explain the logic of this. As we said, we were putting a vertical section through and perpendicular to the layouts or the footprints, both top and bottom, and of course, through and perpendicular to the miter lines. Originally, that section was placed here where you see the green line. And that section, the whole section being placed here vertically, was dropped and projected onto the layout by dropping that vertical and making it a horizontal layout. And this red line, it will be the line representing the projection of the top layout, leaving the green line to represent the bottom layout. The last thing to say about the making of the tilt line is the beginning of this should be at the intersection of the bottom footprints to the intersection of the top footprints. Done with this, you can see and measure the angle of the tilt line against the horizon. Let me conclude by saying it can be an infinite reasons for us to find compound miters in corners or units.
Bill, can we stop it?
This is only one example.
Okay, can you go back 15 or 10 seconds at least?
Okay.
Okay, something that I want to say, guys, is, you know, this is the area where it can get really confusing, but, and this plane, this line, it could be, when I said that this line represent a section, a vertical section on this, a vertical section on this floor plan. As if you put a knife onto like if you put a knife onto and crossing and dissect, going through the 2 layouts. And then once you have that vertical section, which is resting on the same level as the bottom footprint, you're going to drop that section and hinging, or you're gonna drop that section and make it horizontal. And the distance, as is shown here, the distance between this line and this line is the 3 inches that we've been using from the beginning right here. And once you have those 2 lines, once you have the projection horizontally of what it was, the vertical section that we did first, then you have to think, okay, now I have the intersection of that with the green line of the layout or the footprint, and this is my beginning. This is my the point on the earth, or the point at the bottom. And otherwise, what I'm saying is don't start here. No, go with the intersection of the green lines, which will represent the original point at the bottom, and then you're gonna go to the intersection of the red lines. So in other words, don't do the opposite, that you're gonna cross from green to red to green and red. No, this is the beginning, and then you make that line. And as you remember, this is this little line represent a horizontal at the bottom, and that's where your angle is. And that is the angle of your, that is the miter angle that you need in order, cutting miter parts is just a matter of putting it's a matter of putting the extrusion that you're using, or that the extrusion that you're gonna be cutting, onto a table. And normally what we do is we make cuts, and simple cuts when there are the straight cuts both ends. But when we have a miter, we make a the saw is going to contain two different things. It's going to contain an angle of miter for the miter, and if it's compound, it's going to contain a tilt for that compound miter. Go ahead,
Okay.
Bill, continue.
The angle of the tilt line against the horizon. Let me conclude by saying it can be an infinite reasons for us to find compound miters in corners or unions, and this is only one example. The goal of this video is to point that with the use of AutoCAD, you can manipulate orthographic projections to find information that seems to be hidden, or that otherwise you can only find by using trigonometry or with the use of 3D CAD. If you watch this video and came to the end and did not understand any part of this concept here explained, you can call me to schedule a one-on-one Zoom meeting to go over this application step by step. I will be very happy to help. With this, we have finished this training video. My name is Mario Coel. Thanks for watching.
And that was the end. Let me ask you guys, did you get the concept?
Hey, so
Clearly.
Mario, the 3 inches, is that the height of the horizontal?
The 3 inches, it could be the height of the horizontal, or if most common, what the horizontals that we use normally, they are 2.5.
Right.
They can be 3, or they can be even more, but the 3 inches is just a separation that you choose if what you're looking for is the miter and the miter, the angle in the miter, and the angle in the tilt. It's the 3 inches was just something that I picked to separate the footprints vertically. And like I said at the beginning, that separation can be 1 inch, can be any unit, 1 inch, 2, 5, 10, whatever you want. But the more separation, of course, that line, when you're reading the tilt, that line is going to be longer, that separation is going to be bigger, the angle is going to be the same. Either you use 1 inch or 3 inches for the angle in the miter and the tilt.
So you had that diagonal dimension, that dimension should be the same as that separation. Like on your example, it was 3 inches. It has to be the same.
Once you choose a dimension for the separation, everything that you're going to be using is the same. And even to the last time you use that those 3 inches in this case is when you drop that section that it was originally placed there in a vertical plane, and you dropped it to make it a horizontal in the horizontal plane where you can read all the information that you're looking for.
So are those dimensions, like the miter angle and the tilt angle, is that the projected angle or is that the blade angle?
So, I'm sorry, can you repeat that question again?
On your layout, you showed the miter angle and the tilt angle.
Uh-huh.
Are those the projected angles
Yes.
or
they
are they the blade angle?
That is exactly the angle that your blade is going to need to be tilt in order to make that cut. Yes. So like I said at the end of the video, guys, if you happen, and practically this application can be done in the main reason for this video is to tell you that practically in order to find those couple of pieces of information that you're looking for when you have a compound miter, you can apply projections, and in this case using the using the AutoCAD, which is exactly the same way as if you grab the information that you have at hand and you start solving triangles, which it will be in a trigonometrically way to do it, which I will make in the near future. I'm gonna make a video that is gonna be showing you how to solve and how to get that information with trigonometry. But the main thing, guys, is that if you ever come across a compound miter and you see that it's not exactly the same how do you call it, situation that we displayed in this video, give me a call and I'll tell you and I'll show you how to apply this concept into any other situation that you may have that is requiring a compound miter.
Hey Mario,
So
I have a question. In the future, when you've decided to retire, can we add your phone number onto this video?
Absolutely, sir. It will be a pleasure to make contact with you.
So Mario, can you use that same layout to figure out the compound miter on the, like say the verticals, the corner vertical?
Yes, definitely. It will be another way of projecting different views, but yes, it is practically the same.
But the 3-inch dimension would turn into like your bottom of vert to top of vert, right?
Exactly.
It would be 180 inches or something instead of 3 inches.
Any, if you want to use, as a matter of fact, I used to use 2.5 simply because so the people that is getting the explanation or the point that I'm trying to get across, they can see that I'm using something that is tangible in the system that we are using in order to fabricate the elevations or the material that we are fabricating. But in this case, I thought, okay, 3 inches is going to be okay. It's just a round number. Like I said, it can be a unit of whatever dimension you want. But once you pick that unit, again, a fraction of 1, you will stay with that, giving separations to your projections.
Hey Mario,
Yes, sir.
I think we need part 2, man.
What it will be part 2?
Yeah, calculating the length.
And what was that?
Calculating the length.
Oh, yes, calculating the length will be a different, how do we say, again, a different set of steps. However, in there, something else is coming across, which is in order to calculate the vertical length of those parts that we're gonna be cutting miter at the bottom and at the top and all that, we also have to take in consideration that, for example, there was a point in which we start encapsulating the members that we were cutting, and this is vertically, encapsulating those verticals, like putting those verticals on a table on the side. But if you have, let's say, something like this, in which you have to encapsulate that image into a rectangle. And this is what Johnny and where they used in order to put all the tags. Because at the beginning I was using the points in which it was the longest point and the longest point at one end and the longest point at the other end, and that was it. But then I noticed that they were saying no, the length should be this, and then there was a point in which I didn't understand how they entered this to do their drawings, and it was because of that. What I just said, if you have something that is like a rhomboid or a diamond shape, that diamond shape, you have to put it onto a rectangular area in which the longest point may change from the longest point to the longest point may change because of that rectangle. Johnny, do you know what I'm talking about? Okay.
No, I remember we were
At the beginning,
having a lot of discussions about it.
Yes.
Yeah, that you have to kind of project the whatever. So you have to make the shape as a rectangle, kind of pretend that it is rectangle all the time. Yeah.
Mario,
If you
part two.
if you go to
Part two.
the parts library, just draw a rectangle around it, and that's your corners.
if you can go to a part, oh yeah, please.
I mean, I'm just going to like any part. If you go to the parts library, the way it's oriented
Mhm.
on there, just draw a rectangle that encompasses that entire profile. And when you do your calculations, your long point might be in one of those corners that's not physically on the part. And I think that's where the discrepancy was before, when we were trying to figure out the lengths, was your long point was in space.
Exactly.
Which is on the space trace, but aligned to your dimension point.
That is
If you're
correct.
using a box.
Yeah, I said rectangle is actually a box, because the part that we are talking about is a three-dimensional part. Yeah, it will be a box.
How about that, Mario, part two, man?
Okay, Romy. Yes, actually, before that, part two that you mentioned is going to be another way, just simply by solving the triangles one after one, and to get to read those two pieces of information, which is again the miter of the pieces that are coming into this miter corner, and the tilt in the saw, which is the tilt of your the tilt in your the tilt is an imaginary plane that, if you are talking about solids, that is the plane that it will be right in the in a union, right in the angle or the plane that is bisecting that, practically bisecting that corner. But again, guys, also I said that in the video, the reasons why we have a compound matter, it can be an infinite way of reasons. As a matter of fact, you may remember, Chris, when we had those sunshades for the Santana Row. This was a segmented portion, and in between verticals, we have these sunshades where they were sloped. So the ends, each end was a compound miter. And again, it can be solved with simple projections, and that will give you the tilt, and that will give you the length and the angle for the miter cut. So guys, that's it for now. And again, take my word, the offer, if you didn't understand something out of this or included in this video, give me a call. We can get a one-on-one meeting, and I can explain to you, which it will be much better for you guys. So I can explain to you this until you really understand the concept. And the beautiful part of, once you understand the concept, is that you can apply it to different ways of, or to different problems you have, knowing that how can I extract those two pieces of information. But if you apply that to other situations, it's just a matter of applying the concept in how to get there by projections.
Well, thank you, Mario. This is going to be helpful for sure.
Definitely, guys.
Thank
Okay.
you, Mario.
Thanks,
Okay.
Mario.
Thank you, guys.
Thanks, Mario.
for watching.
Thank you,
Thank you, Mario.
Thanks, Mario.
Good job, Mario. Thank you.
Thanks, Quinn.